Thank you for joining Cylance today. In just a moment, our guest speaker will be starting. As a quick reminder, the webinar will be recorded, and also submit your Q&A questions in the Q&A box located at the bottom of your screen. Rob, shall we get started?
Sure. So, good day, everyone. Good morning, good afternoon, good evening, depending where you are. I'm Robert Portvliet. I'm a technical fellow at Cylance, and I lead our professional services team focused on embedded IoT and hardware security. So we do penetration testing and reverse engineering of embedded systems of all types and classes. And today what I'm going to do is talk about a bit about the embedded IoT kill chain. So that is the process in which we and which attackers and researchers of all stripes reverse engineer and attack these systems. So basically how we find vulnerabilities in them, write exploits, and exploit said systems. So with no further ado, let's get started. So quick little safe harbor slide here. We'll talk about first, we'll do a little introduction into embedded and IoT and the difference between the two and some different types of embedded systems and the IoT architecture. Then we'll move into the kill chain itself and the various phases of that. And then we have 3 case studies that we'll talk about because everyone loves story time. So these should be fairly entertaining and educational. And then we'll talk about how some of the ways that we can correct these sort of problems that we'll discuss. So firstly, very quickly, embedded versus IoT, because these terms get used interchangeably a lot. What are the difference, right? An embedded system is just that. It's a system, right? A combination of hardware and software that performs some sort of function, right? It's generally a microcontroller and associated flash memory embedded in a larger system that does something, generally something in the kinetic world that performs some sort of function, right? IoT is not a device, but an architecture, right? Generally, it's a cloud-based back end with devices connecting to it in sort of a client to server architecture, right? And these can be, any kind of sensors, actuators, or other devices, right, that talk to this cloud backend. So the takeaway there is the difference is a single system, which may or may not be networked, right? An embedded system doesn't have to be networked, versus an architecture in which these devices, these embedded systems are in fact networked. So, although you can't really answer right now, right, how many embedded devices are in your home right now, if you think about that? Well, as you can see, quite a few, right? From consumer grade hardware, your cable and satellite TV box and cable modem, smart TV, and your gaming console, your home automation systems, such as thermostats and smoke detectors, lighting control, your alarm system, your doorbell, very popular now, and your, Nest cameras, etc., right? Also though, your HVAC, right? Most modern systems and water treatment systems are embedded systems and are increasingly networked. One thing you might not consider is the your automotive factor, right? Your cars, right? Your average modern car has over 80 to 150, generally about 100 really, ECUs in it. Each one of those is an embedded system, and a vehicle is largely a rolling network with ingress and egress points, Bluetooth and wireless, 802.11 wireless and cellular, a network being the CAN bus, and each one of those being an individual node on that network, right? Something else to consider is medical devices, right? Wireless insulin pumps and continuous glucose monitors, or implantables like pacemakers or ICDs. Or cochlear implants, right? These are all embedded systems as well, and are again, right, increasingly networked in ever expanding fashion. So the business environment, right? So what about your business environment? Well, in most modern, office buildings or commercial buildings, you have building management systems, and these handle everything from the fire alarms to the surveillance systems, CCTV, to HVAC, plumbing and lighting control, right? So really all these aspects of the building are controlled by embedded systems and are, again, increasingly more and more networked with various types of networking, Ethernet to wireless. They also pull in, lower bandwidth wireless technologies like Zigbee, and you see that it's with its counterpart in home automation with Z-Wave, right? So, the takeaway there is that, all these systems are embedded and increasingly networked as well. And then very quickly in a hospital environment, right? Again, these are all embedded systems, right? Infusion pumps, ultrasound, X-ray systems, MRI, patient monitors, right? And while they have been embedded systems for quite some time, right? What we see now is that the market, because of market demands, manufacturers are adding more and more network functionality into these, including, IoT fashion, cloud backend infrastructure, right? Or supporting backend infrastructure that they are hosting, right? Whereas, these systems, up until recently, were not, that network didn't have that much network functionality. They do now, along with associated functionality like over-the-air updates, right? So the point here, right? Embedded IoT devices are everywhere. They are becoming increasingly embedded. Ha ha ha. Pause for applause. Embedded in our lives. They really far outnumber any other type of computing system. By order of magnitude, really, but only a small subset of these, as I've said, have been networked until recently. So, as this functionality grows, right, thus does the attack surface, and this is always true, right? The definite truism in computer security, right, is as functionality grows, thus does the attack surface, and we are seeing a significant growth in functionality here, especially network facing. So this, expands the attack surface against these systems, and, thusly attacks that were not previously practical from an attacker's, monetary standpoint will soon become practical. And these are attacks such as, ransomware, right? Crypto ransomware against medical devices, for instance, or automotive or, automobiles. And that is because of the homogeneous nature of these systems, right? One patient monitor from a given manufacturer is pretty much the same as every other one, right? In terms of configuration, operating system. So an exploit found in one works for all. And as this functionality, the level of functionality increases, these attacks will become more practical. And I expect to see, you're going to see a fair bit of this in the next few coming years. Also, again, because of the homogeneous nature of these systems, botnet style attacks against these, causing them to become agents in botnets, right, will also, I think we'll see expand. So let's talk a little about the actual kill chain itself. And this is, how we find vulnerabilities in these devices and exploit them, as well as, how this happens in the real world for any given attacker. So very briefly, understanding the threat vector here, right? An IoT device, that being a device in an IoT architecture, is like a workstation on an enterprise network. It's a node on a network, right? So if you think about it in the way of traditional network pen testing, right? Once you compromise a node on that network, compromise of the entire network or environment becomes much easier, right? The other thing to take away is that, these devices have to authenticate to the cloud and backend somehow. And this is one of the first things we look at when we're dealing with an IoT device is how is it authenticating to the backend, right? And can we get a hold of those credentials? Is it using a symmetric key authentication, right? And if so, what is the privileges of that key? And what does the separation of privileges in the cloud backend look like, right? So, once we have a set of authentication material, right, what do we gain access to, right? From an attacker's perspective, these devices can be easily purchased from eBay, and once purchased, can be reverse engineered at the attacker's own pace, right, to develop exploits. And this is something that I very much try to convey to our customers who are product manufacturers is that what they envision very often is that the product being attacked in the environment that it's being installed in. Well, that's not really the case. The case is the attacker purchases or obtains the device in some fashion and then does their homework at home, right? Reverse engineering it, develops those exploits. And then once they have those exploits, those can be deployed in a live environment in seconds, right? Especially if they enable remote code execution across the network, right? A final takeaway is that, in some cases, we don't even need the hardware, right? The hardware is what the code runs on, but firmware makes its way out there and is often published by the manufacturer, made available on their website, right? And so if you have the firmware, we can emulate this using a tool like Qemu and perform both static and dynamic analysis against it to find vulnerabilities without even needing the hardware to be able to, to exploit it. So this is the kill chain, as I see it, okay? And the first, as in, all good pen tests, no matter what they are, whether you're pen testing, a traditional computing system, an embedded system, or a human or web application, is built on, a good pen test is built on reconnaissance. So we want to learn about as much about the device before we even start, taking it apart, right? Some good examples of that are a good way to learn about a device, especially if it utilizes custom code and other, custom implementations, is patent applications. So you find a great deal from patent applications by the manufacturer. Another is FCC ID. So any device that's sold in the US that uses any kind of wireless communications must be tested by the FCC. They are then assigned an FCC ID, which must be on a sticker on the outside of the device. And the FCC provides a lookup to find the results of that testing. Now, if the manufacturer in question has not made a request for privacy, you can find some very good results there, such as operating diagrams, or operating description of what the device does, engineering documents and block diagrams of circuitry. At a minimum, you'll find what modulation it's utilizing and what frequencies it communicates on, which you can extrapolate a fair bit of information from that. So that's just a couple examples, right? But the idea there is, do some good Googling, look in some sources that you've known to bear fruit before, and see what you can find out about the device, right? The next thing we look at is the hardware. And what we're looking at there is, were debug interfaces like JTAG or serial wire debug, SWD, or BDM, or UART left in place on the board, on a production board? If that's the case, can we utilize them then to retrieve the firmware from the device, or bypass a secure bootloader, or can we edit the boot arguments to give ourselves additional privileges if we're coming in through UART? UART is another interesting interface, the serial interface. And sometimes, depending on the manufacturer's implementation, we can either get, at a minimum, very good debug output out of it, or we may get a shell that requires authentication, or a full unauthenticated shell over serial. So we might get direct access straight into the device. So that's just a few, examples, right? Some others are, does it utilize flash chips that are easily dumped via bus protocols like SPI or I2C? But the idea there is, we want to gain full privileges over the device early on if we can, or at minimum, right, pull the firmware out of it if we don't have the firmware. And then, firmware extraction, right? The first thing we do is extract the various componentry. And this would include the file system on any kind of Linux-based device, right? And what we want to find there is what code is custom to the manufacturer, right? What code have they written, or what libraries are they utilizing that might have vulnerabilities, right? What have they hard-coded into it, like hard-coded keys, credentials, private keys, which you find fairly often, right? But then what we're going to do is analyze there to look for vulnerabilities in that code. And you can, again, as I was saying earlier, emulate that firmware to perform dynamic analysis against it. Couple that with static analysis of the binaries, so disassembling them and looking for vulnerabilities in them. And giving you some ideas, what we look for there is things like bash injection, especially through like CGI on CGI functionality on embedded web servers, which you don't really see in enterprise environments anymore, but has made a big comeback, so to speak, in embedded systems. or, traditional buffer overflows through the use of insecure functions from the standard C library. A lot of what we find is that, basic exploit mitigations are not enabled on these devices or not present. So, where stack-based buffer overflows have not been seen quite often at all in traditional enterprise computing, right? They're back again, once again, in embedded systems and fairly common. Due to the lack of just basic defenses like DEP or ASLR. So some of the things we're looking at is the network side then, right? We look at the protocols that these devices speak to their back-end systems, right? These devices very seldom operate in a vacuum, and they have some supporting systems or cloud back-end. So what we're looking at is firstly, is a proprietary protocol in use, or is a protocol that uses weak or no encryption at all? Can we thusly do a man-in-the-middle attack because of a lack of integrity protection, right? So can we manipulate data in transit? To give you an example, one thing we've found is pretty easy to do is manipulating data between patient monitors and the central monitoring workstation at a hospital. Because they are UDP-based protocols that do not do any kind of integrity check. We can cause the values displayed on the central monitoring system at the nursing station to be whatever we want them to be. Can we do replay attacks, which often cause a crash in a lot of embedded systems because they don't understand how to process data they've already received and they default to falling over, sometimes in spectacular fashion, actually. And could we do impersonation? What we found in a lot of medical device ecosystems as well is that the devices identify one another through UDP-based broadcasts. And if you know how to speak the correct exchange, they will treat you as a device in that ecosystem and thusly communicate with you, often sending you useful data. So those are just a few examples there. Application layer, right? What we're looking at there, as I was saying, we look at embedded web servers, look for injection opportunities. So bash injection is one where these network-facing services, very often embedded web servers, are calling operating system utilities and passing arguments to them, but not handling those arguments safely. If we can gain control over them, we can then piggyback additional commands onto there and then perform actions on the operating system under whatever privileges that service is running under, which we find is often root. Another common situation is unauthenticated APIs, where there's an API on the device or it's supporting systems that requires no authentication at all. We see this often with WebSockets as well, where by observing what the device or the supporting system is doing across the network in terms of requests, right, we can mimic those in code, make the same requests, and then attack that application. And finally, back-end systems. Again, as I was saying earlier, right, what we're looking at there is the authentication mechanisms that are utilized for the device or devices to authenticate to that cloud backend or whatever backend infrastructure it's utilizing. There's several different things you see. Direct cloud connection is one, and APN is another, or VPN. And I'll talk a little bit about those in a minute. And then also, how is the device segmentation being handled? What does the device, when it authenticates, have access to on the back end, right? Where are those trust boundaries? And, what level of privilege is each device assigned, right? So assuming compromise of a given device, what level of access does that device gain you to the cloud or back end systems? So I know that was a little bit wordy, and I tend to get into the weeds a bit. So now let's jump a little bit into 3 case studies. So these are 3 different embedded systems that we had exploited during engagements. Obviously, it's been anonymized, but I think it conveys the point quite succinctly as to different types of vulnerabilities that you encounter. So the first was a ICS system. This is a ICS gateway that sits on the network edge. It aggregates the comms from all the centers in a data center, sensors on critical equipment, and then communicates with the cloud. So it allows for remote monitoring and support by that manufacturer, right? So first step was we utilized JTAG to extract the firmware from it, right? So we're able to connect up using a JTAG probe, and we're able to communicate and dump the contents of flash memory to extract the firmware. The next thing we did was we discovered that it utilized a hard-coded authentication key. All right. And in this case, so this was a connecting to an Azure backend. So it's used what's called a shared access key, which is a symmetric key authentication scheme. So we found that it connects to Azure using Azure's IoT Hub functionality. Right? And IoT Hub is a framework for managing your embedded systems using Azure. So what we also found was that the messaging format was MQTT, which is quite common, honestly, for cloud communications with these sort of devices. The other thing we found is that, well, let me back up here. IoT Hub nicely has a lot of different utilities that allow you to communicate with it, to allow for management of your devices, et cetera, over MQTT. The one that we used was called IoT Hub Explorer, which was an exceptionally useful little utility. So we took this key and we utilized it to connect up to the API, an IoT Hub. And what we found was that the key had access to send commands to all the other devices of this same type. So basically every device that utilized this key, we were able to communicate with. We were able to list them out, and we were able to monitor traffic in real time going through them. But the other thing we found was that we were able to send a variety of commands to the devices. And so what we're able to do there is craft an MQTT message to shut down all devices. So just basically send it to them and shut down. The other thing that we found was that it was also possible to delete devices. Through a bit of interesting behavior, we found that once you deleted devices, it was very difficult to get them back in also. So that's just an example of, an attacker who obtains one of these devices, in this case, right, extracts that key, and does their homework, can then cause, a fairly significant denial of service against thousands of systems that monitor data centers. So the second case study here is a case of automotive telematics. So this is a device that plugs into a vehicle OBD2 port. It's one of those devices from your insurance provider gives to you to monitor your driving habits and spy on how good you're driving or how badly. Thusly, it has direct interface into the vehicle CAN bus, and we found that it speaks to it communicates over cellular link to a backend API via an APN, and I'll talk about an APN and what that is in a second. So, firstly, we discovered the device uses an IoT architecture and uses an APN backend. An APN is short for an access point name. It is a gateway between a cellular provider's network like AT&T or Verizon and another network, right? Often, in the case of consumer electronics, it's just a gateway between that network and the internet. But that is not always the case. It can be a private APN, in which case it gives access to a private network, right? So what we did was used SPI to dump the contents of the flash chip. And a flash chip on it that was just a WinBond flash chip with a SOIC form factor. It's just an 8-pin, very basic flash chip, right? SPI is a bus protocol. Used for the chips on a board to communicate with each other. And you can use it to read out a flash chip. So we used a tool called the Bus Pirate, along with a tool, software known as Flash ROM, just to pull the contents out of the flash. And what we found was that it wasn't actually the firmware, that the code that ran the device. That was actually an onboard flash on the microcontroller. But what we found was this stored data only. In fact, it was the chip that stored the data about your driving habits, by the way. But beyond that, it contained an XML file. And in that XML file, we found a private APN name. and credentials for that APN and an FTP server as well. So we found credentials, the APN name, the credentials for the APN, and then an IP address and credentials for an FTP server. So at this point, of course, we were quite intrigued. So the other thing to take away from this is, by the way, it utilized a 2G connection, which is basic GSM, right? And GSM has a ton of vulnerabilities in it. One of them is that the cell tower, sets the rules in terms of encryption. So if I'm the cell tower, I can tell that the connecting device or phone, I don't do encryption, pal. And then the device will say, okay, we don't have to do encryption. And then I can monitor everything going through it. And we can do that with a device like a USRP or any kind of software-defined radio, along with software packages, open source software like OpenBTS, which will let us become a cell tower, basically. Now, note, this is not it's not illegal to do, really, in the way that the FCC frowns upon you messing with cellular communications. So we always do this in a Faraday cage environment. Basically, we use Faraday material in order to create a Faraday cage environment in a room where we're not messing with the cellular network. Anyway, but a digression there. So what we did was we used the cell modem, and we dialed up, connected to that cellular provider's network and to that APN. And once we gained access to that APN, what we found was we were on a privately addressed, so an RFC 1918, 192.168.1 network, which was the manufacturer's network of this device. Once we were there, we went to the FTP server, and the FTP credentials got us access. And what we found there was that this was the server that the device used for its over-the-air updates. So it was doing over-the-air updates over FTP, which is bad in and of itself, in that it's plain text communication. But what we also found was that the firmware was unsigned. So unsigned firmware means it's not cryptographically signed, and it can't be verified by the device. So if there's no way to verify it on the part of the device, right? What we could have done was backdoored that firmware, modified it in whatever fashion to perform whatever malicious action we chose. And the next time that the devices did their over-the-air updates, they would receive our firmware and thusly perform whatever malicious action we chose. And given that they have direct access to a vehicle's CAN bus, we could have done some very interesting things. We obviously did not do this because these were live devices in the field, so we didn't actually perform that action. However, you can see the potential for exceptional disruption there, right? Okay. So our final case here, this is a medical device stress testing system, actually, that we were testing on behalf of a provider, so being a hospital, right? They were considering utilizing this device in their environment, and they wanted to know what risks were inherent therein, right? So it was configured like it normally would be operating in the environment. And what we found was, well, firstly, it connects to a database server to transmit patient data. All right, so it's connecting up to other systems using, AD credentials, right? One would assume, and that database server is joined to Active Directory as well. So sorry, I'm getting a little ahead of myself there. So firstly, we were digging around on the file system, and first thing we found was a set of encrypted credentials in a configuration file. And we could tell that they're encrypted because usually encrypted credentials generally have been base 64 encoded afterwards. They look a certain way. Actually, let me back up. Actually, they were not base 64 encoded in this case. What we noticed was they didn't look like hashed values. They looked like encrypted values. And then we noticed character repeatings amongst the different sets of different passwords in the same spot. Now, a pattern should never occur in good encryption. So we were thusly intrigued that, something is odd about this, right? And the other bad thing about encrypting credentials is if you encrypt something, so hashing is the preferred method, right? Hashing is a one-way mathematical operation. You can only hash something. You can't unhash something, right? But if you encrypt something, to be able to decrypt it, you have to put a key somewhere. So you have to use the key at some point. So the first thing we do is go look for the key, right? In this case, though, what we're finding, all right, getting ahead of myself again, sorry. So the first thing we did was we went to the binary that we believed handled these credentials, the main executable for this application, and we reverse engineered it, performed static analysis in order to understand the decryption algorithm, right? And what we found was the encryption algorithm is just a simple substitution cipher, almost like a Caesar cipher, right? And it basically went like this. If you picture in your head, if you're familiar with ASCII tables, the ASCII value of a given character in the password, you compare that to, you take its associated decimal value. And if that decimal value is less than 34, you add a certain value to it. I believe it was 224. If it is greater than 224, you subtract a certain value from it, right? After this, with your resulting number, if it's an odd number, you add 4, and if it's an even number, you subtract 4. And that was the entirety of the encryption that was being done. So once you know this, right, you can do it with a pen and pencil. In fact, one of the guys we work with can do it in his head. Rather talented. But the point here is that, those are hard-coded values, right? So, or rather, wherever this, this encryption's in use on any of these devices. So once you understand it on one, you could use it anywhere, right, is my point. And you can do it with a pen and pencil. So we decrypted those credentials and we used them to access the database server, since this system talked and had, these credentials were for the database server. What we found was that the account had admin privileges on the database server, and also that database server contained lots of PHI, or personal health information, not only from this device, but from lots of other systems as well. So it was a great source of, personal health information. Had we been an actual attacker, that would have been quite valuable to us in and of itself, right? The other thing we found is that since now that we're an administrator on that system, we're able to scrape the credentials out of memory and use those to compromise other systems. So using a tool such as Mimikatz, right, we can scrape credentials straight out of memory, and thus we did, right. And what we were able to do was, within a couple other hops, we were able to gain access to the domain admin account and thusly full control over the domain. It's often been my experience that from your first compromise, your first system that you gain access to on a network pen test, it's less than 3 hops from system to system to gain full control over the environment. And thusly, this is because of credential reuse. Once you have a set of credentials from one system, you utilize them to gain access to other systems, and then you rinse and repeat. Scrape credentials from those, use those to gain other systems, and it basically snowballs into gaining full access over the network. So, given what I've talked about how we attack these systems, and about the case studies of how we compromise 3 different types of systems, right? How do we fix this, right? Firstly, from a manufacturer's perspective, when I'm talking to our clients that are product manufacturers, I tell them you need to design devices with the assumption that the attackers are going to get access to the firmware, right? And this doesn't mean that you can't put as many roadblocks in their path as possible, right? You want to raise that bar against attackers, right? If your attacker is going to compromise your device, you want to make them work for it, right? If you want them to get, you'll have to assume they'll get access to the firmware, but let's make it tough for them, right? But let's design devices with that assumption, right? So firstly here, one part that's critical is a secure development lifecycle, right? To ensure that we have a secure device design and that we're able to verify that during the design process. And then anytime that we are making major revisions to said firmware or software, right? That we are once again verifying that we are following the secure process, right? If we need to store sensitive authentication or encryption material on a device, we want to do it with a trusted platform module, right? And this is a high security chip, almost it's a high security microcontroller, right? That makes it very difficult to gain access to these sort of keys, right? But what the takeaway there is we want to store them in a secure fashion, right? So we can't just extract them from a device and then reutilize them to compromise the supporting systems. Per device key provisioning, so that if we compromise one given system, right, we can't utilize that to compromise all the other devices as well, right? A big one is signed firmware that is verified by the bootloader. So we want to cryptographically sign our firmware. And in the context of a firmware update, right, we want to verify that firmware on the device before we apply the update. And then on boot of the device each time, we want the bootloader to cryptographically verify that signature, right, to ensure that it will only load trusted firmware, right? And this is that chain of trust that starts with the bootloader. Disable debug interfaces in production devices, right, such as JTAG, UART, SWD, BDM, all of those, right? What happens is that these are put in place on prototype devices and then left in place on the production run, right? And those should be removed, and not just the pins or the interfaces, but the pads themselves, because from an attacker perspective, it's only a little bit more work to solder pins onto those pads, right? So they can't be left in place on the board as well. And then a secure supply chain, right? So two areas here. Secure supply chain, both in software and hardware, and a knowledge of your software and hardware bill of materials. That is assuring that the components, hardware components that you're utilizing to construct your device or manufacture your device don't have any known vulnerabilities in them, such as susceptibility to fault injection or side channel power analysis, and that the software libraries and modules that you're utilizing for your product, right, do not have known vulnerabilities in them, and that you also have a way to update them through the over-the-air update process on a regular basis when vulnerabilities are discovered, right? Most products do utilize a significant amount of open source third-party libraries and modules, and we want to make sure that the security of those, firstly, that the manufacturer has an accounting and knows what they're utilizing. Secondly, that those are secure. Tamper prevention mechanisms are good, appropriate to your threat model, right? So if you're utilizing a high security device, it may make sense to use things like case switches, epoxy over critical components, et cetera, right? This might not be appropriate to consumer device because, again, it's not appropriate to your threat model, right? But they are useful in the right context. And then finally, segregation of back-end systems, right? This again goes to, for instance, the per device key provisioning, where if the attacker gains access to the back end, right, what do they see? Are they able to access and compromise all systems, right? Or do they only see a small piece of that back end, right? So we want to, segregate those trust boundaries, right? By way of telling a very brief story, right? One time we were dealing with a piece of ICS equipment. It utilizes a VPN connection to connect to the back end. We gained access to that, and what we found was we're not only able to compromise the system that was providing monitoring for that particular ICS system for that customer of the manufacturer, but those of all the other customers as well, and that was because of a lack of segregation on the back end. So hopefully I've been pretty good with time here. I think we're at about 40 minutes. So that is pretty much it, and now I'll stop and take Q&A.
Thank you, Rob. Thank you all for joining us. And we do have a couple of questions that came in. Mm-hmm. And the first question is, if I am interested in talking to someone about evaluating the security of my IoT devices, what's the best way to reach out to your team?
Let's see. That is actually an excellent question. Question for sales. I should have put actually what we're going to do is, can you guys provide my contact info to the participants?
Absolutely. We can definitely do that.
All right. That'll be excellent. What you can do is reach out to me, since I lead that team from a services perspective. And then I can route it to the appropriate folks, and loop in the appropriate sales folks. But I'm happy to, make that initial connection.
Excellent. Thank you so much. And then we have one more question, and that is, how does a typical project work and how long?
So typically, I would say the average project length for a device that is, not an exceptionally simple nor complex device is about 2 weeks in length. We deliver the report an additional 2 weeks from then, from end of testing. Typically, what we'll do is we'll have an initial call with you to understand what about your device, about what your concerns are about it, your motivating factors. We'll scope it out in terms of complexity and functionality. We'll provide you guys with a statement of work custom written to that engagement, so specific to that device. And then once the engagement is underway, we'll have a kickoff call to discuss the cadence of the engagement and what we will require. Typically, what we'll do is ask for the firmware up front so we can get started working on that, on dynamic and static and dynamic analysis of firmware. And then we often will ask that you can ship the device to our lab because we have a plethora of equipment here, and it's the easiest way to do testing. However, if you prefer, we can come on site. We will, once underway with testing, provide you guys with updates daily on the progress of the testing. So that is what we had done that day, what we'll do the next day, and what findings, if any, at that point we have had, what we have discovered, and we'll provide that throughout the engagement. We'll provide you guys at the end with a technical report, and the technical report covers an executive summary, and that talks at a very high level about what was done during the engagement, what we did, how we did it, what we discovered, how we discovered it, and why that matters, and what the impact is to the security of the device, and what an attacker would be able to do with it, which will be the same thing that we do, honestly. It will also provide finding blocks for each of the findings that we've discovered, each vulnerability, and that'll talk in great technical detail about what we discovered, how we discovered it, with the impact, right, and what we were able to do with it, how we were able to exploit the device. We also provide, screenshots that describe the process of how we were able to exploit it, as well as proof of concept code. So for each vulnerability we discover, we're going to provide you proof of concept code so that you can recreate it in your environment and also assure that you've remediated it, right, for testing and QA purposes. To the same token, we provide a detailed analysis of attack that talks about, in great technical detail, the entire engagement, right? The whole process of what we went through, kind of what I was talking about earlier, right? And we talk about not only, what we did and what worked and what we were able to do, but what didn't work and why, right? So, it talks in great detail about that. And then also, we like to provide positive findings as well. So these are aspects of the device or its environment that were positive security findings, right? Things that you're doing right? We don't like to just point out what you're doing wrong. We like to show, these are positive aspects of the device's security as well. I'm sorry if that was a little too detailed, honestly. Feel free to ask a follow-up if you want me to kind of narrow down on anything.
Thank you, Rob. It looks like we don't have any more questions, but I just have a quick housekeeping is we will be sending out the recorded webinar. And if you would like to reach us, we'll also be including Rob's contact information. And also join us next Tuesday, the 23rd at the same time at 11 a.m. Pacific time. And our next topic that's part of our Cybersecurity Awareness Month will be the real deal about AI. So Rob, thank you so much for joining us. And we look forward to having you speak at a future webinar.
Thank you very much. And once again, if you can provide the attendees with my contact info, if you have a question you want to take offline or you'd like additional context, please feel free to email me. I'm happy to chat. And thanks, everybody. Have a great day.